Hello, everyone, and thanks for joining us. The conversation about explainable AI today almost always includes references to SHAP, methods that fall under the classification of removal-based explanations. Removal-based explanations identify the important features by removing and measuring the impact on prediction. Interestingly, we're going to talk about the work that analyzed 25 different methods that follow that approach. And we're going to be discussing questions as to what are the common patterns between these methods, what are the choices and assumptions made by many of these explanatory methods. My name is Al-Sherif, and I am a steering committee member at Aggregate Intellect. Today, we are very pleased to be hosting Ian Covert. Ian is a PhD student in computer science at the University of Washington, where he works on machine learning research with his advisor, Soo-In Lee. His research focuses on developing rigorous foundations for explainable AI, particularly as it relates to game theory and information theory. He has previously been a student researcher at Google AI Health and a quantitative research intern at Goldman Sachs and Societe Generale. Ian will be presenting his recent paper, Explaining by Removing, a Unified Framework for Model Explanation. It is a highly interesting presentation, and I'm looking forward to it. To the audience, please post your questions in the chat, and we will be asking your questions immediately after the presentation. So without further ado, I will now turn the presentation over to Ian. Please take it away.
All right, great. Hi, everyone. Thanks for coming. I'm Ian Covert, PhD student at the University of Washington. And like Ali said, the subject of this talk is our recent paper, Explaining by Removing, a Unified Framework for Model Explanation. So this is a paper that we published on arXiv just a couple weeks ago. So if you find the talk interesting, you might consider just reading the whole paper, but fair warning, it's a little bit long. So this will serve as a good intro. So here's a roadmap for the talk. We'll more or less track the contents of the paper. But before jumping in, I'll start by motivating this area of research a little bit. So with modern machine learning, black box models are becoming increasingly popular. And we've shifted towards these models, and I'm talking about decision forests like XGBoost, neural network models like CNNs. We've moved towards these models because they offer better performance. And in some sense, that's kind of the most important thing, or it often is. But there's been some reluctance to begin relying on models that we can't really understand. We can't understand how they make their predictions. So the field of explainable AI provides tools that give a solution to this problem by giving some degree of transparency into how models work. And explainable AI is becoming more important as machine learning and AI become more widespread. But if you, as a machine learning person, at some point train a black box model and you want to deploy it, and you need to provide transparency to your users or people within your organization, you'll confront this question: which methods should you rely on? And when you look into this, you'll discover that you have a lot of options. There are hundreds of papers on explainability, and every method gives a different answer about how the model works. You don't need to look through all these methods. The point is just that there are a lot of them. And understandably, it's not easy to navigate all of the options and understand the pros and cons of different methods. So this made us ask ourselves, is the field in a good place, the field of explainable AI? And the first thing to say is this is an important problem. It's to some extent a new one, and researchers have made a lot of progress in a pretty short amount of time. So that's great. But we should also acknowledge some problems. The field is fragmented. There are hundreds of papers. They're all over the place. Methods seem kind of unique and unrelated. So the field is just very disorganized right now. I'd say that's the state of the field. And it's also growing fast. Papers are coming out faster than I believe many people can keep up with them. For people who really focus on explainability, they have a chance. But for practitioners, the field is just kind of exploding right now. And I think within these papers, there isn't a lot of discussion of the underlying principles that connect large groups of methods. There's maybe an incentive to write a paper and contribute a new method. But for whatever reason, there haven't been a lot of papers that talk about how many methods rely on the same underlying principles. So with this talk, we're going to try to fix some of these problems. The first thing we'll talk about is a new unifying theory that characterizes about 25 existing model explanation methods and makes it really easy to understand all of them at once through a couple of shared elements. And I hope that with this perspective, you'll look at these methods, and I'm talking about LIME and SHAP, but also many others, instead of viewing them as monolithic algorithms so that you're just choosing between one or the other, you'll understand that these are very similar methods and they're making basically interchangeable choices. And in talking about this, we're going to delve into one key idea about how to explain machine learning models. And there are other approaches, but the approach we're going to be digging into is removing groups of features to understand their influence on the model. Okay, so let's talk about what this unifying framework is. The title of our paper is Explaining by Removing. Maybe it's a catchy phrase, but what does it mean? So we began by observing that many methods implicitly are simulating feature removal. And by that, I mean, when you evaluate your model and you give it access to all of the features, it makes certain predictions. But it's kind of an intuitive idea to say, what if we imagined that the age feature or the blood pressure feature didn't exert any influence on the model's predictions? What if we removed them in a sense? By seeing how the model's predictions change, we can understand what influence those features are exerting. And a lot of methods are based on this principle. But removing features is maybe surprisingly, maybe not, it's a non-trivial operation. The API for most models is that they require all of the features. So you can't just not give them access to a feature. And for that reason, there are different approaches that different methods take to simulating feature removal. And given a convention for removing features, when we look at all of these methods, you'll see that there are further differences in how they remove features and aggregate the results of removing different features to generate the final explanation. So the point is that there's a lot of diversity within these methods that simulate feature removal. And we kind of figured, if they are all based on feature removal, can we figure out a framework that allows us to characterize them all at once in a really simple way? And here's the framework that we designed or discovered that captures all these methods. It shows that they're all based on different combinations of three choices. So here are the three choices. The first choice is how to remove features. Here we have some kind of black box model. You put features into it and it makes certain predictions. And like I said earlier, you often cannot just not give the model access to certain features. XGBoost, it doesn't allow that. Neural networks don't allow that. Maybe you could just replace the features with default values. But default values aren't neutral, they are values. So there are different approaches to removing features, and how you do that is your first choice. Your second choice is what model behavior to explain. So as you remove different features, the model is going to make different predictions, right? But you have to choose, what it is you're going to look at, what aspect of the model's behavior you want to explain. So are you going to explain an individual prediction? Are you going to explain how the loss evolves for an individual prediction? Or are you going to explain how the model's performance across the entire data set evolves as the different features are removed? That's your second choice. And there are a couple different options. The third choice is a summary technique. So given a convention for removing features and given a model behavior that you'd like to explain, you can see what, let's say you're looking at an individual prediction. You can look at what that prediction is for an exponential number of sets of features, right? Because for n features, there are 2 to the n subsets. And you learn a lot about how the model works by looking at all those subsets, but it's just too much information to convey to a user. It's 2 to the n numbers, right? That's too much. So every method that we're going to talk about has some kind of summary technique that collapses all of that information into something concise for the user, like attribution scores for each feature. So let's just look at each of these choices a bit more closely. So when it comes to feature removal, we're typically beginning with a model, and many of these methods are model agnostic, so we don't need to say what kind of model it is, but it's a model that operates on a specific set of features. So it looks like this. It's a function that can operate on any input in the input domain, capital X. But to remove different features, as in to imagine that certain features are not exerting any influence, we introduce this notion of a subset function that in the paper we denoted with capital F that accepts a feature subset, as in not all of the features. And without going into the details of how we define that, I think the notation is pretty intuitive. It's a function that takes a subset of features where you have X, which is an input in the input domain, and S, which is a subset of the feature indices, where we have D features. So every method, by choosing a way to remove features, is implicitly defining one of these subset functions that says how the model will make a prediction given a subset of features when the remaining features are held out. Okay, now for the second choice, you're choosing what model behavior you want to explain. So like I said, when you have all of the features, the model will make certain predictions, and there's a little animation coming. When you remove a couple features, the model's predictions will change. And you can look at what that prediction becomes for every subset of features. But you need to choose the target quantity that you want to explain. So, like I said, you can look at an individual prediction. And here, with the notation, you'll see it on the left-hand side, we have a set function. It's a function that takes a set of feature indices, and it returns a number, a real valued number, that in this case is the model's prediction given that set of features. Alternatively, you could look at the loss for an individual prediction. And again, this is a set function, but this time we take the model's prediction given that set of features and we put it through a loss function with the true label y. And there are a couple other different options, but one last one is you can look at, to characterize the model across the entire data set rather than for an individual prediction, you can look at the population loss when the model is only given access to a set of features. Okay, so that's the model behavior choice. And the third choice is the summary technique. So in the previous slide, remember, we showed that when you choose a feature removal strategy, and when you choose a model behavior to explain, you are implicitly choosing one of these set functions that says what the model's behavior is for every subset of features. And ideally, you would be able to communicate to the user how the model's behavior changes for every subset of features. But since there are 2 to the D subsets given D features, it's just too much information. So the role of the explanation, oh, by the way, I have this little graphic that I want to show you. With a set of features that's going into one of these set functions, you can kind of think of it as a company with a set of employees. And for every set of employees, the company has some degree of profitability. So if you remove a couple employees, the profitability changes. If you remove a couple more employees, the profitability changes again. And like with explaining how a model works, if you want to explain how the company works and what every employee's contribution is, well, it can be genuinely complicated. It's not as simple as like the employees have additive contributions, because that's not necessarily the case. So if you want to summarize everyone's contribution, you might need to take a lot of information, collapse it down. And that's the role of the explanations in all of these methods. It's to provide a concise summary of this underlying set function that represents the model's behavior as every possible subset of features is removed. So there are a couple different summary types that I think we should distinguish between. The first one is a feature attribution type of summary. And in this case, the format of the explanation that's provided to the user is every feature gets an attribution score that's a real number. And it sort of says, this is the contribution that is made by this feature, or this is its degree of influence or its importance. And we'll see that there are different ways of assigning these attribution scores. But just as a couple quick examples, remember with the company, for every set of employees, there's some degree of profitability. One way that you could quantify the employee on the top left, his contribution to the profitability, you could define it using this technique that we call remove individual, where you look at the difference in profitability when you have all the employees and when you remove just that guy. As another example, you could do this thing that we call include individual, which is where you look at the difference in profitability between when you have no employees and when you just add that guy. Those are two ways of calculating attribution scores. You probably have this instinct that this isn't accounting for employee interactions very well. So there are other techniques that are maybe more conceptually appealing, but just wanted to give you a couple examples. And then instead of feature attributions, there are also methods that as a summary technique do a feature selection explanation, where instead of giving every score a feature, they just indicate a set of the most influential features. And there are different ways of doing this, but just to show you, the explanation will look like this. Instead of giving a score to every feature, the explanation will just say, these features or these employees are the biggest contributors. Okay. So now that we've talked about this framework and we've showed that the different methods are specified by different combinations of these three choices, let's put the framework to use. We're going to look at a couple of example methods and see how they fit into the framework, what choices they make. So we'll start with Lime. And the interesting thing about this is, there's a whole paper about Lime, and it has tons of citations. There's lots of interesting content in there. But with this framework, we can kind of distill the paper down to three simple choices. And just with that, we'll understand Lime. But I am going to spare you some equations because I think that'd be a little confusing. If you're really interested, you should check out the paper. So for the first choice, how to remove features, Lime, at least when it's dealing with images, replaces the held out features, like a big superpixel from an image. It will just replace those pixels with some default value. It'll turn it gray or it'll turn it black. So Lime deals with missing features in a very simple way. The model behavior that is explained is an individual prediction. So Lime, if you look at the paper, it's often used to explain which regions are important in a classification for an individual image. So that's the choice that it makes for what model behavior to explain. And for the summary technique, Lime, of course, gives attribution scores to every feature. And the way that it does that is by fitting a linear model, a weighted linear model, to the underlying set function. And the paper describes in a little bit more detail how you can see that. Of course, you know that Lime is based on fitting a linear model. But if you check out the paper, you'll see how it's actually fitting a linear model to that set function that is implicit in Lime. So that's the Lime paper in a nutshell. The method is really just this. So next, talk about SHAP. SHAP is also a very famous paper. I imagine many of you have heard of it. And once again, we're just going to boil the whole paper down to three choices. The three choices that define SHAP as an explanation method. So when it comes to removing features, SHAP marginalizes them out using a certain distribution. And there are actually two different distributions you can use, but we'll not go into too much detail with that right now. The model behavior that is explained is an individual prediction, and that's the same as Lime. And the summary technique that's used is the Shapley values of that underlying set function. And SHAP kind of famously was one of the first papers to really frame explanation methods in terms of set functions, which are known in another field as cooperative games. But the point is, SHAP, like Lime, can be boiled down to these three choices, and you can see that it's sort of, you can start with Lime and just change two of the choices and you get to SHAP. And from SHAP, we'll go to the next method, Sage. This is one that Scott, Suin, and I introduced earlier this year. It's a little bit like SHAP, but rather than explaining individual predictions, it seeks to explain the model's behavior across the entire data set. And we can understand it as kind of a slight change on SHAP. So here we go. When removing features, Sage chooses to marginalize them out, similarly to SHAP. The model behavior that's explained is the dataset loss, as in the model's performance averaged across the entire dataset. That's what's different from SHAP. But when it comes to the summary technique, it uses the Shapley value of the underlying set function, so a different set function than SHAP, and that's how it gives attribution scores to every feature. And in this context, the attribution scores represent each feature's contribution to the model's accuracy. So a big score means that that feature is providing a lot of information and it's improving the predictive performance of the model. Whereas in SHAP, we're explaining individual predictions. And lastly, we'll just talk about one other method that is kind of similar to Sage, permutation tests. This is a pretty famous one. Leo Bremen wrote about it in 2001. When removing features, they are marginalized out according to their marginal distribution. That's similar to Sage. And the model behavior that is explained is the dataset loss. So as you remove a feature, how much does the model's loss change? And the summary technique is, instead of the Shapley value, it's the remove individual strategy, the one that I showed you with this cartoon a couple slides ago. So with all of the features, the model achieves an accuracy of maybe 90%. And when you remove, say, the age feature, the accuracy drops to 85%. Well, the delta between those two is how permutation tests will assign attribution scores to each feature. So we went through this process over and over, and we discovered that at least 20 methods, I think the count we give in the paper is 25, fit into this framework. So with this table, you can see in every row, we list a different method, and in the different columns, we indicate the three choices that they make: how they remove features, what model behavior they choose to explain, and the summary technique that they use. So we're boiling all of these papers down to three simple choices. So with this framework, we're connecting about 25 existing methods, methods that on their own can be a little complicated to understand, but now you can understand them all at once. In this class, we have both local explanation methods that are explaining individual predictions and global explanation methods that are explaining the model's performance across the entire data set. And we're also including feature attribution methods and feature selection methods. And I know I mentioned all this before, but the point is, it's kind of hard to talk about these different methods at once. You don't see that in a lot of papers because the methods are just doing very different things. But this is a framework that lets us capture a big chunk of the explanation literature. So another thing that you can do once you've identified the choices that all of these methods are making is here we visualize what we think of as the space of removal-based explanations. So for each method in the class, we place it into this grid where along the vertical axis, we've listed the different feature removal approaches, and along the horizontal axis, we've listed the different summary techniques that can be used. And we colorize the methods to indicate the model behavior that they're explaining. And yeah, we just place all 25 of those methods in the grid. And this is interesting because you can see methods that are neighbors are similar. They're making similar choices. If two methods are in the same row or the same column or even in the same box, then you know that they're making some similar choices. And a lot of these connections were not talked about in the original papers. You can also see that methods that are spatially isolated are pretty unique. They're trying things out that other methods haven't tried, so that's kind of interesting. And in every grid cell that's empty, that's a new method that anyone could create. It's a method that hasn't been invented yet. In some cases, maybe for good reasons. In the paper, we actually implement many methods in this grid. We kind of try to fill out the grid and kind of compare the methods. But yeah, it's pretty interesting. You can see that there are tons of methods that just haven't been explored yet. The space of removal-based explanations remains sparse. And there are some parts where the literature is really focused, maybe for good reason. So I just want to say on the note of implementation, our paper comes with a GitHub repository. And the purpose of this repository is to show that we can have a very simple implementation that allows you to run all of these methods. Before this, if you wanted to run SHAP, you go to the SHAP repository. If you want to run Lime, you go to the Lime repository. You want to run Sage, you go to the Sage repository. But here, we have a very modular implementation that focuses on these interchangeable choices and lets you run really most of these methods. So you just choose how you want to remove features, you choose what model behavior you want to explain, and you choose the summary technique, and it generates the explanation. So the purpose isn't necessarily to replace the original implementations, but it does show that because conceptually the backbone is very similar for these methods, you can have a very simple shared implementation. Okay, so let's just summarize what we've seen so far. We've talked about a new class of methods that are based on feature removal. We call these removal-based explanations. Each of these methods is specified by 3 choices: how to remove features, the model behavior to explain, and the summary technique. And the framework that we've laid out gives a great degree of flexibility. So if you have a model and you want to do a removal-based explanation, there's a lot of flexibility in how you want to create your method and in the explanation that you'll eventually get. And to transition into what we talk about in the remainder of the paper, I think this kind of leads to 2 key questions. The first one is, if all of these methods are based on feature removal, it's important to know if feature removal is a smart approach for explaining models. So we're going to address that one. And we're also going to address if we have to make a choice in each dimension of the framework, it would be good to know if there are right choices for each dimension. So we won't take too long with these, but let's start by talking about why feature removal is a good idea. Okay, so the first thing to say about why feature removal is clearly it's intuitive to a lot of research groups, because with a certain degree of independence, we've seen that there are like 25 papers that are relying on feature removal, even though there hasn't been a paper up until this point that talks about, the idea of feature removal at a high level. So clearly there's something intuitive about this, because there are a lot of research groups that have gravitated towards that type of solution. But we should also think about, why that is, what feature removal really means. And this is something that maybe hasn't been talked about so much. Feature removal is a form of counterfactual reasoning. And when you think about counterfactuals, typically the way that it's discussed is, there's a set of facts that occur and that leads to a certain outcome. And by changing certain facts and observing how the outcome changes, you can learn something about the mechanism of the world. But with feature removal, what we're doing is we're not changing what was observed, we're undoing the act of observing some information. And the idea of imagining that something didn't happen and then seeing how the outcome would change is anchored in the social sciences. In psychology, that idea is known as a subtractive counterfactual, and in philosophy, it's known as the method of difference. So I don't know if this is going to be convincing to a lot of people. You're probably already convinced when I tell you, if you want to understand the influence that is exerted by a feature, just remove its influence, see how the model's behavior changes, and that tells you how the feature is pushing the model in a certain direction. That's pretty intuitive, but this is just to let you know that it's also an established idea in psychology and in philosophy. Just to say a couple more words about counterfactual reasoning. So, like I said, counterfactuals are typically changing aspects of a situation to see how the outcome changes. Here, we're changing the observation of a feature value. But alternatively, you could understand a model by changing its inputs, just changing the age feature or the blood pressure feature and seeing how the model's output changes, right? So to depict this graphically, imagine this is our function. Here's an input and the corresponding output. We would learn something about the function if we knew that by changing just one feature, we could achieve a different outcome, right? We would learn something by that, but it doesn't really clarify the whole function surface. It doesn't even clarify the model's dependence on the other feature. So these types of explanations are a little bit limited because, to really understand the function, maybe we should perturb the point in every direction. But how do we summarize that? How do we communicate that to users? I think it's pretty clear that for most high dimensional functions that are nonlinear, it would be pretty complicated to explore and then summarize a function with this strategy. With feature removal, we're doing something pretty different. It's still counterfactual reasoning, but it's a different type of counterfactual, and it gives a more practical way of exploring and summarizing a complicated, nonlinear, high-dimensional function. So that's all I'm going to say now about why feature removal. Now let's move on to the question, are there right choices for each dimension of the framework? So I'm just showing the framework here again. There are these three choices that you have to make. And right is a strong word. I think it would be more fair to say that every method has something to offer. Between different methods, there are conceptual trade-offs and there are computational trade-offs. So let's not say they're right choices, but there are choices that maybe can be interpreted using like more established ideas like information theory and other methods that maybe appear a bit more heuristic because they're making trade-offs that make them faster to run, but maybe they don't mean something as well grounded. So let's just talk about these dimensions one by one. When it comes to feature removal, the choice that you can make that we explore is marginalizing out features with their conditional distribution. And I'm going to spare you the equation here. I'll flash it on the next slide. But marginalizing out features with their conditional distribution, it's a way of removing features that's actually kind of difficult to implement. If you really understand what it means that you need to know an exponential number of conditional distributions. So it's hard to implement directly, but as we show in the paper, there are a number of approaches that methods currently take that provide good approximations to that. And that's important because if you remove features this way, then the explanations that you get are information-theoretic, as in the explanations that get returned to the user. You can say that those mean something in terms of mutual information or KL divergence or pointwise mutual information. And that's kind of valuable because we want an explanation that really means something. There are an infinite number of heuristic ways of explaining a model, but it's nice to know that it really means something. So I'm going to say a little bit about the conditional distribution removal thing. If you haven't thought about this too much, here's one way of thinking about it. So with the chest x-ray, let's imagine you go to the doctor and you show them your x-ray and they say, I think you have a problem. Well, to understand where your problem is, you could mask out different parts of the image. And if you mask out some part of the image and they say, well, with this, it actually looks like you're fine, then you know that that region that you masked out is where the evidence is of your disease, right? But when you mask out some region like this, how do you want the doctor to interpret that? Do you want them to think, oh my God, you have a black box on your chest? There's either something wrong with the machine or there's something seriously wrong with you. You don't want them to interpret it that way. You want them to think, okay, you're just not showing me what's there, but given everything else that I know, I can imagine what's there because of the alignment and because I can maybe see evidence of the problem somewhere else on your chest. So that's how you would want a doctor to interpret it. And this conditional distribution removal approach is kind of doing that for a machine learning model. So mathematically, this is what it is. You're just averaging the model's prediction over different values that the removed features can take on, but you're conditioning on the features that are included. All right, and this is just a table. I'm going to just flash this. It shows that for these different methods, it shows how each one can be interpreted in terms of something information theoretic. Now, for the model behavior, the second choice that you have to make, we would say that there isn't a right choice. Any choice that you make here provides valuable information about how a model works. Whether you're focusing on individual predictions or the data set loss, it's a range of perspectives that tell you about how a model is operating. So the choice that you should make kind of just depends on your use case. We'd say there is not a right choice here. When it comes to the summary technique, well, to compare these different choices, the different choices that you can make here, it turns out that it's helpful to know they all have some precedent in cooperative game theory. The reason that's interesting is in cooperative game theory, they've looked at different ways of allocating credit to players in cooperative games or set functions. And they've identified lots of different properties that different techniques can satisfy that you might want your explanation technique to satisfy. And just to cut to the chase, the Shapley value is a summary technique that satisfies most of those desirable properties. And the other techniques that methods use, they do satisfy some subset of the properties satisfied by the Shapley value, but not all of them. So maybe there are instances where you wouldn't want to use the Shapley value, but it does satisfy a lot of nice properties. I'm just going to flash the equation here. But you should check out the paper if you want to learn more about it. And like I said, because all of these methods have some precedent in game theory, here we lay out for all of the methods what they're connected to in information theory. It's not just the Shapley value. All of them have some kind of precedent in cooperative game theory. Okay, so with that, we've gone through everything that I wanted to talk about. So I'm just going to give a couple concluding thoughts and then open it up to some questions. So with this paper and with this talk, we've tried to present a new perspective for understanding explainability tools. And one of the big messages here is that when you want to use an explanation method, you're not just choosing between LIME and SHAP. With this framework, we've showed that there's actually a whole space of explanation methods that you can use. And with this flexibility to answer really any question you want about how a model works, there's now this responsibility to think about what question you really care about so you can use the right explanation method. And hopefully this will help practitioners do that. We've also tried to develop some more rigorous foundations for these explanation methods. They're not purely heuristic. They're grounded in psychology and information theory and cooperative game theory. So hopefully that will increase some trust in some of the methods that are well-grounded. And just really big picture, we hope that this informs practitioners who are trying to decide which methods to use. And hope that it guides researchers in fruitful directions. So yeah, with that, let's open it up to some questions.
Thank you, Ian. I appreciate it. This is the Q&A portion of the session. We received a lot of questions, so we're going to try to get to as many of them as we can, and we will follow up with those who we did not address their questions after the fact. So the first question we received from Peter Condon. The paper makes reference to the feature removal principle is flexible enough to explain virtually any function. To what level of precision does this extend? Is it capable of, are some of these methods capable of detecting one pixel attacks, or are some of them better than others?
Okay, yeah, that's a good question. Well, okay, so machine learning models are just functions, really. So to fully understand a machine learning model is to understand how every input maps to its corresponding output. Mm-hmm. And I guess detecting one pixel attacks is to my knowledge, seldom the goal of an explanation method. So I guess I would say that removal-based explanations, and that describes a big chunk of the explainability literature. There are other chunks of the explainability literature, but I think all of them are making some compromises in terms of how much information they're going to convey to a user. So, detecting all one pixel attacks, all possible one pixel attacks, sounds like a kind of Herculean task for any explainability method. And removal-based explanations, like any other, I think will kind of fail in that respect. They're not going to, they'll provide some degree of transparency into how a model's working. They're not going to identify all one pixel attacks.
Okay, thank you, and that's very insightful and gives us a really important perspective here. So another question from Peter is, in the paper there was a statement, an explanation that paints an incomplete picture of a model may prove to be more useful if the user can understand it properly. He definitely agrees with that. Now, his question is, in cases where the complete picture is needed, for example, in debugging a model after you've identified that it's biased or overfitting, is it more appropriate to use something other than removal-based explanations, something that's model-specific, or something that's more geared towards relying on the structure of the underlying model, versus a post hoc method, which removal-based explanations are? Yeah,
well, I don't know. I think it really just comes down to what, like I said at one point towards the end of the talk, removal-based explanations do provide a great degree of flexibility to explain a model using a different perspective. And another way of saying that is every removal-based explanation answers a particular question about how a model works. And if the question you want to answer is, related to what are the maybe unfair biases that my model has, or what features is it overfitting to, are there features that really help in the train set but not in the test set? For some of those questions, removal-based explanations provide a really good answer. For other questions, maybe they don't. It really comes down to the question that you want to answer. The thing that we really wanted to say with this thing that you quoted about how an explanation that paints an incomplete picture may be more useful to some users. What we wanted to do there is say that there's a big spectrum in how much information your explanation conveys, right? And if you wanted to convey all the information, then you would provide some crazy high dimensional plot of how every input gets mapped to every possible output. There's no explanation better than that, right? But that's too much information to absorb. And with removal-based explanations, there's basically a range of how much you want to compress down that information to give something to the user.
Okay. Thank you. That makes a lot of sense. So we have another question from Rahil Ahmed from the ExplainX team. He's asking, saying that the unification methods are great and helpful, but how do we decide when to use each method? Are you offering any guidance, if you will? Which of the set of methods that you've examined are better under which conditions?
Yeah, so a good way to think about that is to disentangle. I'm not going to say SHAP is the best method or Lime is the best method. Let's disentangle them. Think about each of the choices individually. If we, for example, let's look at the summary technique. There are a bunch of different summary techniques that you can use. And for many of them, it's pretty easy to come up with situations where they kind of fall apart and give silly results, like the remove individual strategy or the include individual strategy. Those are two summary techniques that are used. It's easy to imagine cases where they give kind of spurious explanations because they don't account for interactions between different features. So in that sense, it's kind of easy for me to say that something like the Shapley value or the Banzaf value overcomes those problems, and you should be a lot more comfortable using those methods, although they come with some computational problems. So Yeah, I guess like I said in the slide, there may be use cases where you would have some different preferences, but the combination of the Shapley value and removing features with their conditional distribution, I think in a lot of cases will match up with something like what you're looking for from an explanation method.
Okay. Okay. Now, I guess the other question from Raheel was about just taking causality into account. Are there any? Do you have any suggestions or thoughts on identifying causality, not just association, but, when we're looking at explanations, especially in a high stakes decision?
Yeah, that's a good question. A lot of people are interested in merging the study of causality with the field of explainable AI these days. And with this paper, we didn't focus on that too much, but I have been keeping up with some of these papers, so maybe I can say something useful. By the way, there are a couple papers that we cite that do take some kind of causality angle, but what they're really talking about is causality between changing a feature and its effect on the model output. So it's talking about causality in a pretty limited sense. And I think that's probably not what most people are looking for. Maybe they're looking for like causality between the features and the actual response variable, or maybe they're looking at causality between the features. So like if I change this feature, what kind of impact does it have on the other features? And right around the time that we were finishing this project, there's a pretty interesting paper that came out. It's in NeurIPS 2020. It's called Causal Shapley Values. And just to give you a little flavor for that, if you're into causality and you're familiar with Judea-Pearl's do operator, then what that paper does is it basically, again, it fits really nicely into the framework. It's just a different way of removing features. What it does is it says, now if we're going to say that we know these features and we don't know these features, causal Shapley values of this method just says, let's do a Pearlian intervention on these features and kind of account for the impact that has on the remaining features. And then, we'll just follow through with the Shapley value like the original SHAP. So you can bring causality in just like that, just by using it as a different way to remove features.
Okay, excellent. Thank you. That was very helpful, Ian. Appreciate it. Now, the next question we have is from Dylan Slack. He's the author of the paper "Fooling Lyman Chap: Adversarial Attacks on Post Hoc Explanation Methods." His question is, in your examination of removal-based explanations, do you have any thoughts as to their relative vulnerability to adversarial attacks? Are there methods or passive methods that you identified would be more vulnerable than others to those class of attacks in terms of, and that's essentially measured in terms of reliability and robustness?
Mm-hmm. Well, so that paper, that Fooling Lyman Chap paper, if I remember correctly, the angle that they take is they imagine a model with some unfair biases on the data manifold, reliance on features that you wouldn't want to rely on. And their goal is to create an adversary that yields explanations that suggest that the model is, just fine. It's not leaning on those sensitive features. And the way that they do that is by exploiting the fact that Lyme and SHAP and their popular implementations rely on off-manifold behavior. So I forget to what extent they discuss this in that paper, but if there's a reason that they say you can fool SHAP. It's because the popular implementation of SHAP uses a particular way of removing features. It's marginalizing out with the marginal distribution. If you're into this, then you'll probably know what I'm talking about. If you implemented SHAP in a way that it was restricted to on-manifold behavior, and another way of saying that is that you remove features by marginalizing them out with their conditional distribution. And there's a paper that talks about a practical way of doing that. It's called, I think, Shapley explainability on the data manifold. Then I think with that, you kind of wipe out this particular attack. You could not have a model with unfair dependencies on the data manifold and an explanation that gives the opposite answer. So methods that basically use, I think, less heuristic feature removal strategies, in particular, removing by marginalizing out with a conditional distribution, I think eliminate that kind of attack.
Okay, thank you. That was extremely insightful. Got a question from Ziad. He was asking, what is the difference between feature importance that has always been used in the feature at, no, I'm sorry, what is the difference between the feature importance that has always been used and the feature attribution being, no, I think he got that. Okay, that question has been addressed. Maybe the question from Locke, in terms of Sage and say XJ Boost, what is the runtime similar to SHAP, where it is largely dependent on the number of trees or the depth of trees?
And this is a question about Sage?
Yes, yes.
For Sage and SHAP, well, okay, Sage and SHAP are addressing different questions, first off. So SHAP is trying to explain individual predictions. It's like if you go to the bank and they use some model to decide if they're going to give you a loan, and you can ask, well, why don't you want to give me a loan? What is it about my application that makes it look like I might not repay? So SHAP will answer that question by saying, well, let's break it down into your individual features. The fact that you're young kind of makes you look risky. The fact that maybe your income isn't that high because you're a graduate student makes you look like you're a little bit risky. SHAP answers that type of question. Sage, while it is related to SHAP, is answering a quite different question. It's saying your model achieves a great degree of accuracy, right? And that's because you're providing it with good features and the model is exploiting those to make good predictions. Sage answers the question, how do you explain the model's performance in terms of the different features? Which features are providing the most information across the entire data set? So by virtue of trying to say something about the entire data set, Sage is going to be much more expensive. But it's data set dependent. Maybe it's only 10 times as expensive, which is actually pretty good bang for your buck. So, and also I'll say this thing about the trees. Tree SHAP is a model-specific method that exploits the fact that the model is implemented using trees to avoid an expensive Shapley value sampling-based approximation. That kind of thing could be integrated into Sage, but right now Sage is it's a model-agnostic implementation. Which, if you compare kernel SHAP to tree SHAP, kernel SHAP is quite a bit slower on trees.
Okay, so a couple more questions. Appreciate you sticking out with us, Ian, here.
Totally.
What are your thoughts on some of the measures that are starting to emerge or in the literature on the quality of a post hoc explanations? I mean, they're measuring stability, fidelity, the level of agreement between the post hoc explanation prediction and the ground truth versus the underlying model. There are all sorts of metrics that are popping up right and left, and what are your thoughts on how effective or they're good they are in terms of measuring the quote unquote quality of an explanation?
Yeah, so the first thing to say is it's great that people are now putting a lot of effort into coming up with good metrics, because there is a point in the short history of explainable AI that you could write a paper by proposing some method and just cherry pick a couple examples. And thankfully, we're beyond that stage, because if we were still there, then you'd have a lot more papers coming out every day. Now the burden is a little bit higher to say that your method is worth running. And some of the ideas that you mentioned there's a paper on sanity checks that show that you try to make sure that your method is actually sensitive to the underlying model. That makes complete sense. That's great. A method should probably be discarded if it's not sensitive to the model's parameters. A lot of those are great. But for the metrics that have to do with the quality of the explanation, I think those are actually pretty tricky. This is a really tricky problem, because if you really understand what Lime and SHAP are trying to do, just for example, we don't want to walk through all of the methods. Let's just talk about SHAP actually. SHAP, it tries to explain an individual prediction by saying what contribution is made by each feature. So presumably with SHAP, if you took the features with the highest scores and you removed them, then you would see that the model's prediction goes way down because you removed those positive contributors. That should pull the prediction down. And a lot of the metrics that are out there that try to like remove features incrementally or include features incrementally are basically getting at this question of do the scores adequately indicate what will happen as you remove features. And a big problem that I think is kind of unsolved right now is that there's this entanglement between how your method removes features. Like if you run SHAP, when you just replace features with zeros, okay, that's how your method is removing features. Then there's how your metric removes features. Because with your metric, you're going to remove features, and you're now going to look at the prediction, and you want to see if you're removing the top SHAP features, then you want the prediction to go down fast. But if in your metric you remove features by also replacing them with zeros, then you're going to kill it. Great. But I think it's easy to make a method look good by just making your metric remove features in the same way. But what's the right way to remove features? Should you retrain a model with that set of features? Maybe, I don't know. I think these metrics are tricky, and it's easy to put something in your paper, but put something in your paper that kind of satisfies the requirement for having something. But I don't think anyone who like really knows what's up is satisfied with where we're at with metrics.
Okay, no, and that really is a very helpful perspective. I appreciate it very much, Ian. I guess maybe we have room for one more question. Maybe we'll end it on a high-level perspective type question here. Is there a risk, in your opinion, on relying too much on these explanations that we're actually potentially not detecting bias? In other words, are these explanations helpful in finding where bias exists, but they're not really guaranteeing that it does not exist? And are we seeing a risk where people are using these explanations out of context and they're saying, oh, I have an explanation, check the box, and then we're good to go?
Yes, I think there's a big risk of that. And one of the reasons for it is like up until now, I think there's the fact that like everyone's using SHAP and everyone's using Lime, like those two methods have really taken off. I think for a practitioner, it's pretty appealing to just say, okay, we're going to use SHAP. But without like a proper understanding of what SHAP is really doing, and I think, thinking about it in terms of this framework where you have these different choices available to you, really helps understand it a bit better. It's not obvious that SHAP is the tool for identifying unfair biases. In fact, the fact that Dylan Slack has that paper about fooling Lime and SHAP, we now know that SHAP can utterly fail to identify biases. It's also the case that many of the methods that are unified in this framework use feature removal strategies that will, by default, give zero influence to a feature that is not a direct input to the model. So if there's a feature that functionally does not affect the model's output, SHAP will give it a score of 0, and so will Lime. But is that what you want in the context of bias detection? Because what if there's a proxy feature that is correlated with some sensitive attribute? Then maybe the sensitive attribute should be getting some degree of importance. So this is actually one of the things that I'm probably going to work on in the near future. I'm just showing, I think removal-based explanations are very well suited for answering questions about model biases, but you need to think pretty hard about which choices you're going to make. And I think that removing features with their conditional distribution, I don't know how to like describe the whole thing. quickly, but I think, yeah, removing features with their conditional distribution is probably the right approach for bias detection. And if you don't do that, then you can get some really misleading results, and you're absolutely gonna have situations where you could use SHAP to say, like, look, it's all good, we don't have unfair biases, but you easily could.
Okay. So unfortunately, that is all the time we have for today. Ian, I thank you for a great presentation and a great perspective for helping us really better understand the field of explainable AI, and also for your work and specifically. And I thank all of those who joined us online. To see more free content like this, please visit our website at AI.SCIENCE and log in to access slides from this and other sessions. Also, make sure to subscribe to our YouTube channel, ML Papers Explain, to get notified about live sessions and free content that we publish. This concludes our event. Thank you for watching. We appreciate it very much.
Yeah, thanks for having me.